So we are the 5G, 6G versus the EESS Passive Sensors. I'm Regan.
I'm Jerry.
And we're both seniors at Olin studying electrical and computer engineering. Next slide. This is us again. Next slide. So we're going to start with a little bit of introduction about the coexistence situation. Next slide. So here is our scenario. We're in the 140 to 160 gigahertz range, which is in the extremely high frequency. This is also known as the millimeter wave band because the wavelengths are measured in 1 to 10 millimeters. And we are primarily concerned about adjacent band interference. If you look at this lovely graphic here, we can see our EESS, the incumbent is in the green, and then our entrant, 6G, 5G, whoever wants to be in this band, is sort of in the black. They're not going to be in that band because it's protected, but they will be adjacent to it, which may cause interference in the future. Next slide, please. So now we're going to talk a little bit about the Earth exploration satellite services. So these guys basically do a lot of data capture of the interaction between sort of the atmosphere and the oceans. There's a lot of meteorological stuff they do. And this is also used for like environmental monitoring. But it can also be used for meteorology, cartography, and more. And it's a lot of satellite imaging and remote sensing. So our work primarily focuses on the 148.5 to 151.5 gigahertz band, and this is where the passive sensors lie. In particular, these passive sensors take data on the use of stratospheric nitrous oxide.
And here are some images from the EESS. These were presented at a Switzerland conference on ITU and WMO. Here you can see the surface temperature across the entire planet, and you can see North Atlantic sea ice on here back in 2007. Since then, it has likely dramatically changed, but the EESS executes very important imaging of our planet for environmental purposes. On this slide, we're going to talk about 5G. So 5G is the 5th generation cellular broadband network and is the successor to 4G, also known as LTE. It is extremely fast, it is primarily effective in urban settings, and it operates in a similar way to Wi-Fi in the sense that it operates over smaller distances. On the bottom right, you can see different types of cells used for 5G, which can support anywhere from 50 to 250 users and span a couple of hundred meters. So they're really effective in urban settings. And on the top right, on the top left, you can see a quote from T-Mobile. Millimeter wave spectrum has great potential in terms of speed and capacity, but it doesn't travel far from the cell site. It doesn't penetrate materials at all. It will never materially scale beyond pockets of 5G hotspots in dense urban areas. This 5G rollout also motivated the big merger between T-Mobile and Sprint so that they could maintain competition with Verizon and AT&T. Now 6G is the 6th generation broadband cellular network and is planned to be rolled out within the next decade or so. It has some obstacles, such as high power consumption in the 140 gigahertz band, which is our band, and you can see on the left that the power consumption and desired or required trajectory for it to be scalable is lower than what it actually is. Some of the obstacles they're experiencing with this are the lack of availability in the 100 to 275 gigahertz band. On the chart on the bottom, all the green sections are allocated to fixed and mobile communications for cellular technologies, and they don't have a large enough contiguous band in order for 6G to be effectively rolled out in this band for it to be of effective power consumption. One of the big motivations for rolling out 6G is for purposes such as EESS, so that scientists can transmit up to 1 terabit per second of data transfer on terrestrial sites and satellites.
Right, so a little brief timeline. Basically, this is just showing that the EESS has been around for a heck of a long time. They've done a lot of work in this area, and they have had this band for a really long time. And the newer stuff like 5G has just started to come out. Like April 3rd, 2019 was when they just first started releasing it. And 6G has only materials present available right now. There is no real mention about where they're going to be, just a lot of sort of talk about what the technology might look like in the future. So as we can see, EESS has been around for a long time, 6G is just coming in. Next slide, please. And so here's a little bit about the interference geometry. The basics that you need to know is that passive sensors essentially take a temperature reading from the Earth's surface and like what is called a footprint. So that little red circle on the Earth is what they call a footprint. And they're primarily concerned about this because if there are any transmitting stations, so our little satellite button there, if they are transmitting towards the passive sensor, that could cause noise or interference into the data that they are collecting, and that is what the EESS is primarily concerned about.
And now we're going to take a deep dive into some of the regulations around these bands and how they're being used by the players. So for the EESS, we care about the 148.5 to 151.5 gigahertz band. As we stated earlier, is allocated exclusively for passive use. And in the ITU, they have some recommendations for allowing this operation to continue as it currently does. And they have a percentage of area or time of permissible interference that it may be exceeded, which is possible by 6G and other entrants adjacent to this band, but they want it to stay below 0.01% or a tenth of that. So there are recommendations in the ITU to protect environmental sensor monitoring, and this is something that should be followed by other players who come into adjacent bands. Additionally, they have some allocations for 100 to 275 gigahertz, as well as a lot of open space between 275 and 3000 gigahertz. Now, a lot of the space in these bands are a bit more opaque, so interference is minimal, which makes it a potentially useful area for 6G and other players to take advantage of. However, there are still concerns of high power consumption. And on the charts on the bottom and right, you can see some of the molecules used, detected in environmental sensor monitoring, such as bromine monoxide, chlorine monoxide, nitric acid, and you can see all the bands used by the EESS between 30 gigahertz and 230 gigahertz.
All right, so now we're just going to talk about kind of what solutions may look like in this area. So currently right now, passive sensors are treated a little differently from active sensors. So it's a little bit harder to tackle the idea of how do we limit interference for like these passive sensors. Of course, we just looked at the ITU limits and those should be followed as always, but there's also this push for this new emulation software called Coliseum. And there's a push to make it more available into the higher bandwidth ranges. So that way they can do a lot of extensive testing before any of this rolls out to see what can possibly be done. Next slide, please. And so finally, our proposed solution is basically follow the ITU limits. There are limits there that have already been created and these should be followed. So anyone who is in this situation or wants to like be in this band should take note of that and should come up with a plan accordingly with a whole bunch of data and figures to prove that they are staying below the interference level necessary in this bandwidth. I believe that's it.
Here are our sources. Thank you very much.